So we're going to look at our text, which is walking rates. So it says in variables and patterns. Well, we didn't read that, but if you think about a bicycle touring business, you can use tables, graphs, and equations to represent patterns relating variables such as cost, income, and profit. We didn't do any of that. You looked at some linear relationships, like the relationship between cost and a number of bytes. So let's start there. This right here is an example of a linear relationship. It's a linear relationship because relationships are represented by straight lines on a graph are called linear relationships or linear functions. So that's a key idea. We've got relationships. So if you're making notes for yourself, relationships that are represented by straight lines on a graph are called linear relationships. And most of the ones that we will work with will be called, or could be called, linear functions. So, this gives you an example here. The number of bikes. We've got 2 bikes cost a certain amount, 4 bikes cost another amount, 6 bikes look to be about $400, and this keeps going up, and it goes up in a line-like fashion. So some big questions to ask is, how can you determine whether a relationship is linear by examining a table of data or an equation? So what we want to do is we want to be able to give you data and have you decide, is this linear or not? We also want to be able to give you an equation and have you decide if this is linear or not. It then says, how do changes in one variable affect changes in a related variable? So, for instance, we can see that the number of bikes, as the number of bikes increases, the cost increases. So what we have there is we have an increase of one results in the increase of the other. Likewise then, if we started off in the middle here, we would say that the decrease in one causes a decrease in the other. So how are these changes captured in a table, graph, or an equation? So we're going to have to look for those things. And in a graph, it's pretty easy to see, but in a table and an equation, it might not be quite so easy. So this paragraph right here is the start of a series of problems. Mrs. Chang's class decides to participate in a walkathon. Each participant must find sponsors to pledge a certain amount of money for each kilometer the participant walks. Leanne suggests they determine their walking rate in meters per second so they can make predictions. Meters per second is our unit that we're working with, and they want to do this for each kilometer the participant walks. So there's going to be some unit changing. So something to make sure that we know is that there are 1,000 meters in 1 kilometer. Also, because we don't do a seconds a whole lot when we talk about how long it takes to walk a kilometer, there's 60 seconds to 1 minute, and then there's 60 minutes to 1 hour. And these are things that we probably will use to convert things. Now, they have this activity that we're not going to actually do. We're just going to take a walking rate of our own. We're going to pretend like we have a walking rate, and we're going to use our pretend number for that walking rate. So to determine your walking rate, we're not going to do that, but we're going to start here. What's your walking rate in meters per second? We're just going to assume that, let's go with a nice easy number of 3 meters per second. This would actually be pretty fast, but I'd rather use something that we can use now that we're not going to use later. So how long would it take you to walk 500 meters? So what we would do, So part A, we're saying 3 meters per second. Part B, then, we're going to do some math. First one is how long would it take you to walk 500 meters? So if we know 3 meters per second, 500 meters on top over x, so that's 3, this pen does this occasionally, x, and this is 1 second. So we can cross multiply, and that would be 3x equals 500. We divide both sides by 3, and x equals, oh, I wish I had a calculator. I've grabbed my calculator. I'm going to use it. 500 divided by 3 gives us 167.7 seconds. Now, that's a weird thing, but we're going to leave it be because it doesn't tell us that we have to have our answer in any other units. How far could you walk in 30 seconds? So we're going to go 3 over 1 equals 30, and x here, so we cross multiply. That gives us x equals 90. So in 30 seconds, we could walk 90 meters. But they also ask in 10 minutes. Now this is where we're going to have to change things. We're going to change 10 minutes into seconds. So we know that there's 10 minutes for x number of seconds, and so that's 1 minute is 60 seconds. We cross multiply, and so that gives us x equals 600. So we're looking at 600 seconds. So we're going to go 3 over 1 equals x over 600, which means when we cross multiply this, we have 1,800 meters. And then the last one is 1 hour. Well, 1 hour is 60 minutes. And then we've got 1 minute for 60 seconds. So again, we cross multiply. 3,600 seconds in 1 hour. And so then I'm going to do the rest of my work over here. We've got 3 over 1 equals 3,600 over x. Well, x over that. We cross multiply, and we find out that we've got 3 times 3,600. That's 10,800 meters. Describe in words the distance in meters you could walk any given number of seconds. All right, so this is one of those things that we're not used to. But what we would say is, I can walk 3 meters times the number of seconds. Write an equation. Well, that would be distance equals rate times time, and the rate in our problem is 3. And then use the prediction for 45 seconds. So we say 45 seconds is time. So we have 3 times 45, which is 135 meters. So this is the first problem of finding and using rates in our book, Moving Straight Ahead.